Okay, so we've been working with understanding the relationship between exponential functions and log functions. They're inverses of each other. So it makes sense that we're going to use the other one to undo the other. We're going to see our properties of exponents come into play here. Our properties of logs come into play here. The change of base formula, definitely. And so we're going to start today with some exponential equations. Okay, so remember that an exponential equation has a variable in the exponent. We can't really work with it when it's in the exponent. So our goal with all of these exponential equations is to find a way to bring the exponent down. The first one is using this property of exponential equations. And so the property says this: if b to the m is equal to b to the n, then m is equal to n. So does this make sense? If you have some sort of expression containing exponents where you said something like 2 to the x equals 2 to the fifth, well, it follows then that x must be equal to 5 because 2 to the fifth is only going to equal 2 to the fifth. Okay, so the property says if I know that this is true, then I know that this is true. The bases are not canceling out. We're not doing anything to eliminate the bases. We're simply applying a property here. Here's what I see that drives me crazy because it's wrong, is I see people cancel out the bases on both sides. They haven't canceled. We haven't done anything to the bases. We're just applying this property to say, if I know that these expressions are equal to each other, then the exponents have to be equal to each other, okay? Now, it may not be given to you that you have the same base, but we know enough about powers that we can figure some of these out. So, for example, on number 1, it says 5 to the 3x minus 6 is equal to 125. Well, those are not the same base, but I know that 125 is 5 cubed. So I can rewrite this as 5 to the 3x minus 6 equals 5 to the third. Now we can apply our property. If I know that that is true, then I know that these two exponents must be equal to each other. So we simply create a new relationship. 3x minus 6 has to be equal to 3. That's an equation that's pretty easy for us to solve. And we get that x is equal to 3. If you plug that in, we get 5 to the third equals 5 to the third. There we go. Now, number 2, we have to see, can I write 4 as a power of 8? No. Could I write 8 as a power of 4? No. So that means I'm going to have to change both of them if I can. And I know that 8 is 2 cubed. And 4 is 2 squared. So I can rewrite them both with a base of 2, okay? So if I do that, I'm going to write out kind of this middle step here so you see where what we get ends up coming from. So we're going to do 2 to the third, and we're going to raise that to the x plus 2 power. And on this side, we have 2 squared, and we're going to raise that to the, x minus 3 power. Now, properties of exponents, when we do the power of a power, remember we end up multiplying the exponents. So we get 2 to the 3 times x plus 2 power and 2 to the 2 times x minus 3 power. Now, you can skip straight from here to here. You don't need to necessarily write out that blue step, but that's why we end up multiplying the way that we do. Now I have the same base, so what do I know? These powers must be equal to each other. So now I need to solve the equation 3 times x plus 2 equals 2 times x minus 3. So first we'll distribute 3x plus 6 equals 2x minus 6. Subtract 2x, subtract 6, we get x equals negative 12. So that's if you have the same base, you can set the exponents equal to each other. Most of the time, it's not going to be possible to rewrite them with the same base. And when that's the case, we have to use logarithms. Remember, that was the whole point of the invention of a logarithm, is that it undoes an exponential function. They are inverses. So our job is to get the exponential expression by itself. So you might have to do some unraveling on both sides first. Then you're going to take, this says either the common log or the natural log, but we're always going to use the natural log because that's the one we use in calculus the most. Once you have that, you're going to use your properties of exponents or your basic log properties, natural log of e to the x equals x, or log base 10 of x is equal to x, to be able to solve. So remember, our power property of exponents says if I have the natural log of b to the x, we can bring the x out to the front, and that's how we get here. Remember, the goal with exponentials is to release the variable from the exponent so it's somewhere that we can work with it. So for number 3, we are going to start by taking the natural log of both sides. So I'm going to rewrite this equation so that I have a little bit of space to add more stuff in. So I have 5 to the x equals 134. And we're going to come in and take the ln, the natural log, of both sides. When we do that, that allows us to bring the x to the front using our log properties. So we have x times the natural log of 5 equals the natural log of 134. Now remember, we're trying to solve for x. So right now I have x times natural log 5. So to undo that, I just need to divide. Natural log of 5 is a constant. Remember, that just represents a number. We haven't put it in our calculator yet because it's not an exact value. It's like 2/3. You just leave it because it's an exact value. So the natural log 5's divide out, and there's our answer. Now, in my math lab especially, and on the tests, we always want the exact values. So it'll say, give your answer in terms of the natural log. Well, there's the answer. The natural log of 134 over the natural log of 5. Remember, those natural logs don't cancel out or anything because they represent the number. So that's the exact value answer. But then we can go ahead and put that into our calculator to see what we get. And we get approximately... Now, it doesn't tell us how to round, but let's do 3 decimal places. So I get 3.043. So if it asks you for the rounded answer, that's what we want. Pay attention to the fact that whatever it's asking you to round to. Now, for number 4, this would be the rare instance that I would not use the natural log. Because it's base 10, we already know that the common log, if I do log of 10 to the x, what's wrong with my pen, equals log of 8,000, these are going to undo each other. So x is just going to be equal to the log of 8,000, which we could put into our calculators, and that comes out to 3.903. Okay. Go ahead and pause your video, please, and try number 5 on your own. All right, here is what I get, so you can go ahead and check your work there. There's your answer both in terms of the natural log and approximated as a decimal. Now, let's look at one more that has a few more pieces. So here we need to isolate the exponential term. There is also a typo right here. You see we've got too many equal signs. This was supposed to be a plus. I think I just didn't get the shift button on there, okay? So that should be a plus instead of an equal sign. All right, so the exponential term is this right here, e to the 0.6x. So we're going to treat that as the thing we're trying to get by itself, just like with any other equation. So I'm going to start by subtracting 3 from both sides. So I get 40e to the 0.6x equals 234. Then I'm going to divide by 40. So e to the 0.6x is equal to 234 over 40. Notice I'm not going to make that as a decimal because I don't want to round until the very, very end. If I'm going to round, I want to do it one time. Now this one is nice because it's base e, which means when we take our natural log, we don't actually need to use our exponent property because the natural log is going to undo the base e. So when we're going to take the natural log of this side and the natural log of this side. These are going to undo each other, and we're just left with 0.6x equals the natural log of 234 over 40. Okay, now we're also not done in this case because we still haven't solved for x. The last step here is going to be to divide by 0.6. So you see all the different places we would have had to round. This is why we're waiting until the very end. So now we're ready to go ahead and put that expression in our calculator. Make sure this time when you do the natural log of 234 divided by 40, don't close the parentheses until you've done the divide by 40. So you want all of that in parentheses. So go ahead and type that into your calculator. I'm going to do the same. Natural log, parentheses, 234 divided by 40, close parentheses, then divide by 0.6. We get 2.944. Okay. All right. I would like for you to pause the video to try number 7 and then come back here and see the answer before you leave me for today. Notice you're going to bring down the x plus 2. Bring that exponent down in parentheses because it's a single quantity that's going to matter. So isolate your exponential first and then solve. Come back here in 3 seconds for the work and the answer. All right, hopefully you got to here. Here's a hint. Once you get to here, you can do one of two things. You can distribute that natural log 4 and then solve for x, or we could go ahead and divide by the natural log of 4 on both sides. So we get here, whoops, that's definitely upside down. Hold on. The 19 should be on the top. I don't know what I was doing there. 4 should be on the bottom. And then to solve for x, we would simply subtract 2. So your answer would be natural log of 19 over natural log of 4 minus 2. Now to type this into your calculator to get your decimal, make sure this time that you close both sets of parentheses. And when you do that, we get 0.124. All right, that's where we're going to stop for today. I'll see you next time.